All right. Um, all right, so I'll just jump in. Welcome everyone to this the course, this understanding solar PV permitting and inspecting in New York State. This is a course provided by NYSERDA. My name is Chris Doty. I work at Frontier Energy. We do a lot of work with NYSERDA. Um, they've asked me to present this course. I've been doing it for about a year, so you know, I know the material pretty well, but I'll be presenting to you today. We have a lot of material to cover, so we'll be moving through pretty quick. But real quick, kind of right out of the gate, the purpose of this presentation is to give you a kind of a 10,000-foot view of the unified solar permit and the inspection process, while going over some of the more common errors that NYSERDA's come across through thousands of inspections. It's not really necessarily to give you answers to every specific situation. Obviously, that would take far too long for a 2-hour seminar. But if you do have specific situations that you come across that require additional information, or you need a second opinion, NYSERDA is always there to help with those, or you can email me at this email address, cdoty@frontierenergy.com. If something like that does come up, and I'll be happy to get you an answer. We can go over all the questions at the end. If you have questions, just throw it in the chat, and then we can go through them at the end. If we go through, like I said, this is a pretty full presentation, so if we get through to the end and we haven't gotten to your question, please feel free to email it to me, and I'll be happy to get you an answer. For anyone trying to, or taking this course for code inspector credit through New York, please put your New York State training ID in the chat, because that's how obviously the Department of State allocates credit for the course. So if you don't do that, you risk not getting credit for the course, and I would love for you all to get credit, so please put it in the chat. So this course is valid for 2 hours of in-service training credit, 1 for enforcement and administration, 1 for uniform code, and this is a course number. This is all just kind of paperwork that we gotta go over before getting into the actual meat of the presentation. Another thing, you have to log in between 30 minutes before the scheduled start time or 15 minutes after the scheduled start time. All of you are in right now, so you're good. And then you have to log out between the end time and 30 minutes after the end time to get credit. And you risk not getting credit if you are not within those times. The Division of Building Codes and Standards can't give credit to you if obviously you're just doing other things on your computer, so you have to maintain this as the main screen. Otherwise, the attention to duration ratio goes too low, and you don't get credit. Obviously, if you're getting credit for the course, they want you to be paying attention. But let's actually get into the course. So during this course, we're going to review the New York State Solar Unified Solar Permit. I'm very sorry. Hopefully this will resolve itself. The USP was created by NYSERDA. It's a model permit that kind of helps permitting authorities across the state. Then we'll walk through what to look for in field inspections, what labeling is required, and then we're going to look at some common errors. And as we're offering this course in a webinar format, there are a number of polling questions that will appear throughout the course. I think there's 8 or 9 of them. So keep an eye out for those, and then answer to the best of your ability by putting your answer in the chat. And it's all obviously based on this course, so if you pay attention, you should be able to get them right. And let's jump in. All right, so the New York State Unified Solar Permit. Over 300 communities in New York State have adopted the USP. this is done through an easy process. It can be done by local law or adoption by the local government. And the USP is included as kind of a best practice, and it includes requirements that can be applied to all solar PV systems of any size. It was made originally for residential, but it can be really applied to any size system. Overall, the general requirements for a 5 megawatt system are going to be the same as a 5 kilowatt system on a house. It's just the documentation will be obviously more complicated for a large system. So what's the Unified Solar Permit all about, right? It's a powerful tool. It provides a comprehensive, standardized permit application that's designed to streamline the approval process for installing solar in your community, right? It gives a general framework for how to have a permit application so that it's standardized throughout the state, wherever it's been adopted, which is much of the state. And it allows you to streamline your process without taking shortcuts. It streamlines by making it standardized throughout the state, so all contractors kind of have an idea of what they need to submit, the questions they need to have answered. They need all the information they need from the homeowner, things like that. So it makes it consistent, predictable, and repeatable, and it can be duplicated across multiple authorities so that everyone is looking at the same things, and it can help move permits through more quickly while still maintaining quality. And it can be used by permitting authorities, contractors, the community, basically anyone involved in getting a permit for these these solar systems. And obviously the most important thing for NYSERDA is they want all installations to be safe and code compliant. All right, so let's take a detailed walk through the application itself. Here's the first 2 pages of it are kind of an application. It's kind of like a cover sheet. There's not a lot of technical information in these 2 pages. It's kind of more of a who, what, when, where, and why. And so here's the first section of it. The first thing to do is determine if you're eligible. If you can check yes to all these first 6 questions, then you should be able to utilize the Unified Solar Permit. Otherwise, you may need to go through a different process depending on the AHJ standard permitting process. So, it's things like, does it need historical review, or does it need a special use permit? Is the roof going to be, or is the system going to be parallel to the roof, or is it going to be at a different angle? It specifies, or asks if all the contractor has all licenses required in that jurisdiction, things like that. And permitting authorities can customize this to fit their jurisdiction's need with there's a lot of customizable fields you can see down here. We'll go through those a little bit more. So this section, which I believe is, it's the bottom section from the previous page. This describes the submittal requirements of the application. So this is a place where jurisdictions can customize specific fields, such as like fee schedule, payment methods. You could give information like website and email addresses of important people or important websites to look at. And you can include your information on there, so it's easier for contractors to find as they're going through this permitting process. So the third section down on the first page is where the application spells out approximate timelines contractors can expect for either review and response or review and denial of an application. So, and these important, can keep in mind that these could be 2 different timelines, right? You could get an application, the first page, there's something completely wrong or something that would disqualify it from using this application. Like if one of those first 6 questions was no, then you would deny the application. And so this section kind of gives solar contractors a clear expectation on when they'll hear back from the permitting authority, so that they're not just turning it in and waiting, forever. So here's the first section of page 2. It includes all the basic information you would, logically need to identify the dwelling and the owner of the residence where this will be installed. It's all kind of the basic information you would see in all types of permit applications. It has information on the local tax maps, the section, block, and lot number that would be contained in the municipal tax records. And this is to give the AHJ easy access and easy reference, so that they know, it's easy to find exactly where this is supposed to be going. So the next section is very concise, and it's a clear snapshot of the system, which includes the kilowatt hours DC or kilowatts DC that the system is. That's the size of the system, the type of inverter, and the location of the interconnection. So that would be supply side or load side. We'll get through that a little bit later. But if you know these 3 things, then you basically can know what to expect when you're going through the permit application and looking at the documentation. So you can have, as I said, a supply side connection or load side connection. You can also have a string inverter, DC optimizers, or microinverters. Microinverters are basically, as the name suggests, tiny inverters that are typically attached to each solar panel, and they convert from DC to AC right at the panel. A DC optimizer basically conditions the DC power coming out of the solar panel to be what the string inverter is expecting, and that improves efficiency. And then a string inverter is when you have a bunch of solar panels connected together, and they all go to one central inverter that converts from DC to AC. And as I mentioned, if you know these 3 things, the size, the type of inverter, and the type of connection you have, you can generally know what to look for in the rest of the documentation. So the next section down is kind of detailed contact information for the contractor and the electrician. It includes contractor and electrical licensing numbers where they're needed. It's important to notice that 2 signatures are needed. At the bottom of this application is the property owner and the contractor. And that this is both of them attesting to the accuracy of the information on the application. So you want to definitely make sure both signatures are there. So now that the application portion is filled out, what documents are required to accompany the application? As you can see here, there's 3 pages of extensive information that's required to be submitted to be compliant with New York State laws. There's construction documents and other information that's critical in evaluating the system. And so this is the section that's generally, well, the whole thing is, it's basically the same for 25 kilowatt system up to a megawatt. It's and even more. So it's you can apply this to all size systems. You may have to adjust different pieces of information. There's definitely going to be more information on a larger size system permit application, but you can use this this application for any size system. All right, so a little bit more going through these. There's customizable fields, as I had mentioned, that allow the permitting authorities to add specific local requirements if they have them. For instance, does the AHJ require separate electrical permits, a separate building permit, mandatory planning review, fire department approval, things like that. So this is the opportunity for the AHJ to customize this standardized framework for the specific requirements that they have. and it allows the permitting authorities the necessary bandwidth to ensure they request the information that works best for their departments. And it also, since it's in the standardized framework, it's easy to review, and it helps contractors to not miss anything that is necessary in a given jurisdiction. All right, so the construction documents that are required as part of this package. So we're going to go through these in greater detail as we move on, but the most important thing with these documents is you want to make sure that they are stamped and signed by either a New York State registered architect or a New York State licensed professional engineer. And so this is, again, this is that professional taking responsibility for the quality and the accuracy of the design, along with specifying the equipment and the materials to be used. So, you know, it's the code official's job to determine code compliance, but you I'm assuming don't want to be held liable for a bad design, right? It's not your responsibility to design the system. You make sure that it's installed and everything is code compliant, but you don't want to be taking on the responsibility for the design, because that's the responsibility of the engineer or the architect. So definitely make sure that they're signed by a registered architect or a licensed PE. All right, so now we're going to go through some of the documents that we'll be looking for. Different documents have different things we need to check. So first, the electrical details. What you want to do in this section is you want to go through each and every piece in a very systematic way. If you have multiple, you know, presumably eventually you'll be reviewing more than one PV system at some point. And so you want to have a process where you go through carefully from one side of the system to the other. We'll go through the different components real quick in a little while. But you want to carefully consider each component in the design and detail the specifics to the, you know, make sure that there's specific details in these documents for the local code official to review, which, you know, presumably would be you. And so you want to go either from the modules to the array, at the array to the interconnection, or backwards, and make sure each item is accounted for. There's also going to be a site plan or a roof plan, and this is a detailed drawing which indicates the specific location of all the major components of the system, including rooftop access, setback requirements, where the power meter will be, you know, where the interconnection is, things like that. So we'll go through that in a little more detail as well. And lastly, you have the structural information. And the thing to keep in mind with this is everything in this section is site specific. It's, you know, every solar PV system is different and every roof is different. So this is basically to make sure that the roof can hold the solar PV array and it won't collapse under the weight. You know, super important. And it's, like I said, site specific. It'll take into account the wood used in the roofing and things like that. And it has load calculations with the framing details and quantity and locations of the solar panels, things like that. So, and there's checklists for each of these, the construction documents, the roof plan, and the structural information in the NYSERDA New York State Solar Guidebook, which we'll go over in a little bit. Which inspections are required by the AHJ? So the whole point of this is to clarify the items that are required for the inspections so that there are no surprises. The inspector should not only be looking to see that everything is code compliant, but that the construction matches the proposed design. And the whole point of the unified solar permit is to make it so that this is done in a systematic way to reduce human error. NYSERDA does require also that photos be taken on all the systems that they incentivize, which is essentially all the systems in the state. You can, if you really wanted to, someone could turn down the incentive so they wouldn't have to have pictures taken, but that's typically a decent amount of money, so I don't know why anyone would. But NYSERDA does require that the photos be taken, and that's important because sometimes access is not easy, and sometimes things that need to be inspected are covered up during the installation. So this can help you reduce the number of trips you have to make out to the site, and it can help prove that a safe and code compliant system was installed. So the first question here, so which of these items is not a requirement of the solar PV permit application? A site drawing, B, a wiring diagram, C, proof of payment of property taxes, or D, the contractor's telephone number. You can go ahead and put that in the chat. Give you guys a minute. All right. So since this is a pretty long presentation, we'll keep moving through. The answer is proof of property taxes. Everyone does have to pay their property taxes, but it is not a requirement for this permit application. So we'll keep moving through. All right. So now you've received a permit package. It could be the standard package your department receives, or it could be the unified solar permit. And the tools in this section will help you review the permit package. So NYSERDA has developed a bunch of tools to assist the permitting authorities in their work. There are design review checklists and field inspection checklists, in addition to a quality assurance checklist. And these are available on the NYSERDA website. They're super helpful. They're very comprehensive. They're tools designed by professionals with experience performing thousands of inspections. NYSERDA's done, I think, over 4,000 inspections as of a couple of years ago. So it's much more now. And so they consolidate a lot of that information and put it in these checklists, and it's super helpful. And we'll take a look at each of these in detail. And a lot of this can be found in the New York State Solar Guidebook, which is available through NYSERDA, which you can see here. This is where you would see it, or where you can find it, New York State or NYSERDA.ny.gov/solar guidebook. And so this is a comprehensive and detailed collection of information for contractors, permitting authorities, plan reviewers, and inspectors. And it's continuously updated, and new chapters are being added to reflect changes in the industry. They really are constantly updating it to keep it current. So it's a super useful resource. And I would urge you to, if you do have a PV system that you're inspecting, definitely reference the Solar Guidebook. All right, so for starting with the design review checklist, and there's three main components, which are the construction documents, the electrical diagram and the electrical documentation, and the structural analysis. All of these need to be looked at thoroughly to determine code compliance in the system. And all of these are all, these are screenshots taken directly from the Solar Guidebook. And it goes through, you can see it has kind of a step-by-step way to go through everything so that you don't miss anything. And it's very comprehensive, and it also has code references within it. So that's super handy too. All right, so first we're gonna take a look at the site plan. This is kind of a walkthrough of the components of the system. Excuse me. It has basic equipment information, including the locations of key components and any trenching. It includes setback requirements to help avoid having to remove and replace equipment if it's too close to the property line. And you want to go through each of these things in detail in order to avoid mistakes. Oh, and here's an example site plan. It's not perfect, but it is a site plan, and it'll kind of give you, as I said, it's kind of a map. It gives you an idea of where everything should be located. It gives you distance to the property line of all the major components, and you want to make sure it has the right address, right tax parcel number. You want to make sure that it has the professional designer stamp on the drawing. That's super important. And it has kind of locations of modules, which will be right here, the inverter, the disconnect, the meter, the interconnect, rapid shutdown initiation device, which you can see right here. So you want to know where those things are going to be located when you go out to the site and you can actually inspect the system. It also has the location of rooftop access and ventilation. It has the location of the utility meter, as I said, the distance to the property line, and like I said, you want to make sure it's stamped by the professional. So here we have the electrical checklist. This is a super important part of this. Obviously, electricity is potentially very dangerous. You want to go through every single item in the checklist in detail to make sure that everything is accounted for, or if it's not accounted for, you can make a note and check it when you get to the site. So you want to look at this checklist and then look at the electrical diagram provided by the contractor. Make sure you understand how each of these correlates with this, and then like I said, make note of things that are not included, so that you know to pay extra attention to them during the inspection. So here's kind of an example of if you're going through, you check off things that you know are correct. If something isn't included and shouldn't be, you just obviously mark NA, and they're making notes of things that are not included that should be. So in this one, rapid shutdown is not accounted for. So you'd want to double check that when you're on site. You want to note missing items such as conductor sizing, or if something is not applicable for the system, you'll mark it as not applicable, obviously. And doing this makes it easier for the reviewer to not miss details. These are typically very detailed systems. You want to make sure that you get all the details correct, so to avoid having a system installed that is dangerous. And you want to go through all this prior to issuing the permit. So just more examples of what you're looking for, and how you draw the correlation between the electrical diagram and the information, and then the checklist. And you want to make sure that all the calculations are done correctly and there's no missing piece of information that would be necessary to evaluate the system. All right, so for the structural analysis, again, you want to go through each of these items, make sure all the values are accounted for and the calculations have been filled in and properly done. And again, This is site specific. It's definitely not a one size fits all kind of page. Everything is site specific, so every one of them will be different. And you want to make sure again that they're stamped and signed by the professional engineer or the registered architect. This is just hitting that point home as much as humanly possible. If you do not make sure that these are stamped and signed, and you give a permit, then it's basically you taking that responsibility on your shoulders for the design of the system, which is not where it should be, right? The engineer or the architect is, they're paid to design the system. They should be taking that on their shoulders. And if it's a bad design or something goes wrong, it should be on their shoulders. It should not be on yours. So you want to definitely make sure that they are stamped and signed, so that you're not taking that responsibility for yourself. All right. Hold on. So now that you've gotten through the permit package and you've determined all the requirements have been met, the permit's been issued, and construction is complete. Now what? What's the next step? What do you do now? And also, have you considered the safety of the inspector, which is an important detail, obviously. So inspections are required to follow NFPA 70E, which is the standard for electrical safety in the workplace, and of course OSHA requirements. Everything has to follow OSHA requirements. But NFPA 70E has been traditionally for electrical workers, but now has been updated to include inspections as well. So inspectors have to comply with the standard. And as part of this, an initial risk assessment is required. If the electrical inspection involves removing covers, the assessment will determine if PPE is required or if other methods of risk reduction are required. And it's also important to keep in mind that other job site hazards may be present. I apologize. Then they may be present that may require, fall protection or potentially like eyes and ear protection, things like that. You wouldn't expect that at a solar site, but there could be other things around that need those. All right, so NFPA 70E is, the standard outlines procedures to reduce risk for inspectors and electrical workers through the process. So you first go through a risk assessment procedure, then go through the hierarchy of risk control methods, which we'll go over in a second, to determine what's the best way to reduce your risk. It'll go over how to establish an electrically safe work condition, establish or estimate the likelihood of an occurrence of an arc flash incident. Arc flash is super important because it could cause a lot of damage and it could kill people. So you want to absolutely minimize the risk of that. And then if absolutely necessary, you would select arc related clothing using incident energy analysis method, which is detailed in this standard, to protect yourself against arc flash. Traditionally, it was sort of possible for inspectors to just kind of stand behind someone else who's wearing PPE and have them check things, and you can just write things down. But this is, we're kind of moving into times where those days are gone, and that's probably for the best. You're the one inspecting, so you need to follow the procedures to be safe. And so this kind of details how you can do that. So this is the hierarchy of controls from that standard. It's basically a method of evaluation and selecting the most appropriate method of protection for personnel. So the best control is elimination of the hazard, which, you know, obviously makes sense. For electrical exposure, the best way is to shut off the power, then establish proper lockout tagout and verify that the power's off. So then that makes it so there's less human error involved, and that's obviously better. Then, you know, the next thing down would be to replace the hazard. Then the next thing down is engineering the controls, which is isolating people from the hazard. Then warnings, administrative controls, and then PPE. PPE is basically just you're living with the risk, and putting something on so that it will not be as bad. So that's obviously the worst one. If you can completely shut the system down while you're inspecting it, if you have to get into any of the electrical components, that's definitely the best way to do it. But many municipalities have gone to visual inspections only with no, you know, opening of junction boxes or electrical panels, and this is why, to remove just completely remove the hazard, basically. It prevents people from having to be exposed to the hazards. And this is another reason why photos are required during the installation, because it allows you to see inside some of these things while they're being installed and before they're energized, which reduces the risk to inspectors who are, you know, typically not licensed electricians. So you know, that's kind of the hierarchy of controls and how that's used. So here we have the second question: which of these is not in the one of the hierarchy of controls for electrical safety? And just throw your answer in the chat. Looks like pretty much everyone is getting the correct answer. Yes, C. The one that is not a hierarchy of control is to just reschedule work until after normal working hours, when demand for power is lower, and not a method of, that's not a method of mitigating a hazard. That's basically just saying we don't really care about the risk. We'll just do it when there's not a lot of people around. So that's obviously frowned upon. So now we're going to go through the field inspection checklist. This is an extensive guide on what to look for. It's based on the National Electrical Code requirements, and as I said, over 4,000 detailed inspections. It gives kind of provides a framework for a robust, thorough, and fair inspection process. And it's printable, which means it's super easy to bring in the field and take with you to inspection, so you don't miss anything. So it's super useful, and it's available right here. Oh, okay. So this field inspection checklist provides an organized method of review. You would start at one end of the system and go to the other. You can either start at the array and go to the interconnection, or you can start at the interconnection and go to the array. It doesn't really matter how you do it, as long as you do it consistently. And this will help you move through quickly each time and not make errors if you do it the same way each time, right? The more times you do it, the better you'll get at it, and the fewer errors you'll make. And so we're going to go through a run through of the basic items covered in the checklist. And let's jump in. So first, of course, you have the array, which is essentially where the panels are located. Here's a few examples of different types of array. You have ground mounted in the middle. You have pole mounted on the right, and you have roof mounted on the left. Roof mounted is probably the most common that you'll see. But as you can see, the modules on a rooftop may present additional challenges to inspectors. There could be multiple arrays like you see on this home. They're on potentially steep roofs, which could have access issues. And these are all things that can make it difficult to inspect. So again, this is a great example of where construction photos being provided by the contractor are valuable, and we'll talk about that a little more later. Ground mounted and pole mounted arrays may be easier to access the different connections for inspections, as you can see. So at the array, one of the main things that you want to look for is you want to compare the electrical diagram provided by the contractor and the nameplate information for the actual panels that are on site. You want to make sure that they're identical. As in this example, you can see on the electrical diagram, they have a different model number than was actually installed at the site. And so the reason this is so important is because all of the design is based on the precise electrical characteristics of the module, and the string configuration, as well as the inverter's output characteristics. So if equipment is substituted in the field, the equipment could become undersized for the new electrical characteristics. A good example of this is the max system voltage. The open circuit voltage characteristics are higher for higher wattage modules, or even the same wattage modules from different manufacturers. And all of your circuit sizing, overcurrent protection, etc., were designed based on the energy production from the design panels. And you don't want to just assume that the wiring and the system components are still compatible, because they may not be, and you could be overloading the conductors and melting them and causing fire. So that's definitely something you want to take a good look at. So another thing that you want to look at with the array is the grounding of the array. The grounding and bonding of the array is not only a code issue, but a safety issue. The integrity of the grounding system is vital to any electrical installation, not just PV. And the grounding system in a PV system is dependent not only on the conductors, but also on the equipment itself, which is used to carry fault current to an overcurrent protection device or a fault detection system. In the event that there is a breakdown anywhere along the ground fault path, the fault will not be detected, which can leave conductive parts of the system energized and presents a significant shock hazard. So imagine you have a mason going on the roof to fix a chimney that's in disrepair, and he just touches the solar array, and he could be shocked with up to 600 volts of DC electricity, or potentially more, which would likely kill him. So you want to prevent that, obviously. And it can be prevented by careful grounding and bonding. A lot of systems nowadays have integrated bonding, which would be like this. It's kind of a clamp to hold the panels in place, and it provides a ground path through the system. Many of the newer arrays use this kind of bonding. And you can see over here, you want to make sure that everything is installed in a nice tight manner. This has a screw coming out, which obviously you want to avoid. You want to make sure everything is nice and tight. And in the middle, you can see an example of a ground lug, which is another grounding method you might see. It's becoming less popular than the integrated bonding, but you will still see it. And so another thing to keep in mind is you want to, it's critical that you ensure that the equipment that's used to ground and bond the system is suitable for the environment and the application. If you use if the grounding method you use is not rated for the environment, it can fail. And we'll see some examples of that a little bit later. And that would leave the system energized and dangerous. So still on the array, as I said, it's critical that you use outdoor rated equipment. These are all outdoor because they take advantage of the sun, obviously. And so you want to use outdoor rated equipment. You want it to be able to survive the harsh elements, which, you know, it's outside 24 hours a day, 7 days a week for potentially 25 years or more. These systems are typically warranted for 25 years. So you want to make sure all of the components in the system are going to last that long. And so, you know, it makes sense that the components of the system that are used to facilitate the safe functioning of the system must have a similar lifespan to, you know, the panels and the junction boxes and all that. So you want to make sure the grounding is weather resistant, and all the rest of the components are. So on the left, you can see that the wires are fixed in place with a black zip tie, which is the UV rated zip ties. If you use the white ones, they're typically a lot less weather resistant. They get brittle in the sunlight, and then they eventually break. I've seen them break in less than a year. So definitely make sure that black zip ties are used. And on the right, you can see, it may be a little bit difficult to see, but you can see this screw connecting the lug to the conduit is rusting. That means they did not use an outdoor rated screw. That will eventually corrode, you know, rust away and corrode, and it will likely come disconnected, and then you won't have a grounded system, which is obviously not a good thing. So yeah, that's kind of one of something definitely to look for if someone's taking a shortcut, you know, using a non-weather rated screw. That will eventually cause a failure. All right, so optimizers and microinverters. As I mentioned earlier, a DC optimizer is essentially a DC to DC converter that takes whatever amperage and voltage that's produced at the solar panels, because it varies throughout the day, and it converts it to the voltage and amperage required by the string inverter. Microinverters are essentially an inverter on each panel, like a small inverter, as the name indicates. So all wire runs in a microinverter setup are AC electricity as opposed to DC. And then they bring it all together in an AC combiner panel. So we'll take a quick look at that. They both give module level control, and they have similar requirements in the code. This is the section for that in the checklist. You can see it's pretty short, but they are pretty similar. It requires you to look for not only equipment verification, but also other details like conductor type, proper grounding, etc. And so the notes at the bottom describe important details such as labeling requirements for rapid shutdown. And something to keep in mind is even though microinverter systems meet rapid shutdown requirements by design, they all have it kind of included in them. They still require proper labeling. More on the microinverters and optimizers is so an important element of installing and inspecting this type of equipment is the thorough understanding of the instruction manual, as you can see examples here, which may include specific considerations for that device, such as you know, mounting or bonding and grounding, as well as limitations on string configurations, etc. So you want to familiarize yourself with these so that you know you are aware of the limitations. All right, as I mentioned, one way that DC optimizers and microinverters are similar is the rapid shutdown features. So rapid shutdown is a method in the code where DC conductors are shut down on a level close to the array. If power is interrupted, the system shuts down to prevent live DC conductors in the system or the building. And this is allowable to use in the code as the method for rapid shutdown, right? You don't have to install additional things to achieve that requirement if your system has microinverters or DC optimizers. And so here you can see an example of the proper labeling to meet the rapid shutdown requirements of the system. So here we have question number 3, true or false. Microinverters or string inverters with DC power optimizers. Using those is one way to meet the requirement for rapid shutdown within the code. So you can just throw your answer in the chat. So I think the answer to that is true. Microinverters or DC optimizers used in conjunction with string inverters, they do have a rapid shutdown feature, and they are a valid way to achieve that requirement in the code. All right, so moving on to structural rooftop considerations. The guidebook has a section for rooftop PV attachments and penetrations. In addition to verifying that they're present, you have to verify that they're installed properly. The guidebook gives us examples of the proper installation. You may see flashing that's not installed according to the manufacturer's instructions, things like that. It's important for contractors to follow these guidelines and for inspectors to know what to look for. There's also the New York State Residential Code. There's a roofing section, so and the New York State Building Code for non-residential buildings this is applicable for. And so on the left, this is kind of a weird view of this picture, but the roof is going down to the right, even though it kind of looks like it's going up. But you can see that this flashing was installed correctly. It goes up under the shingle so that water won't, get back up under the shingle, and it'll just flow over the flashing and down the roof. And then on the right, you can see this is the correct piece of equipment that you would use for this, but it's not installed correctly and it would fail. It's pushed down. The rubber boot should be up, kind of like to shed water off of it, but it's been pushed down and water will collect there, and in the winter especially, it'll freeze and unfreeze as it gets warm and cold, and that'll cause damage to this this penetration, and it could cause leaks and things like that. So eventually it'll fail, and so this would not fail, or this would not pass inspection. It's a correct piece of equipment, but it's not installed correctly. So, true or false, properly installing roof flashings and sealing roof penetrations is a critical part of installing the rooftop PV systems. This one should hopefully be easy. Yes, I believe everyone is getting it right. As you would imagine, that is absolutely true. You do not want to have poorly sealed penetrations to, let water get into the house and cause mold and damage and all that good stuff. So good job. All right, so the next part of the system that we're going to look at is junction boxes. This is basically any enclosure that has electrical connections running through it. So if an enclosure is mounted on the roof deck, it has to be properly flashed and sealed. As you can see on the left, this is properly flashed and sealed. A conductive enclosure, which is essentially a metal enclosure, is considered likely to become energized, and it also has to be properly bonded per NEC requirements. This junction box actually wasn't. You can see the green wire, which is the grounding wire, is going right through this this junction box, and it's not bonded to the junction box. So if the sheathing on this wire came, it wore down, this could get exposed to the conductive wire, and it would be conductive at that point, and that could make it unsafe. But if you ground it, then it should still be safe. And in the box on the right, this box is non-metallic, so it doesn't have to be grounded. And in both pictures, the enclosures have to be rated for the environment they're installed in. So now we're going to talk about string inverters. This section of the checklist asks for equipment verification. Is vital to ensure that the actual installation matches the design submitted in the permit package. Construction documents. You want to make sure that the conductor sizing is based on the information provided by the manufacturer, and if a contractor substitutes the inverter model, it can be oversized for the conductors carrying the output current. And this is verified by looking at the inverter nameplate, which is typically on the side or underneath the inverter itself. In this case, the DC conductors are coming down from the roof, excuse me, and you have to verify that they're in metal conduit and that they have this label, this red label, every 10 feet. Obviously here it does, because it's not 10 feet, but you want to make sure that's the case. We'll go over the labeling section a little bit later, and that is included in that. And the metal conduit provides kind of an additional barrier in case of an emergency, so that anyone in the vicinity will not have contact with the DC wiring, which could remain energized even if the inverter shut down. So that's an important part. Here we have a look at the conduit bonding that's crucial to a safe installation. This conduit is bonded to the grounding wire and the grounding lug, so that the whole system is grounded. This has a non-metallic enclosure, which is why the conduit has to be grounded separately. And you also want to check conductor sizing again, and by looking at the markings on the wire, and as well as the fusing requirements. Fuses have to be rated for solar PV, not just for any DC use. And for residential, that's 600 volts solar DC, or 600 volts DC solar, and for commercial, it's 1,000 volts DC solar. So you want to keep that in mind. Make sure that the fuses are actually rated for solar. Lastly, we're going to take a good look at it and verify the labeling requirements per NEC 690. This inverter has a disconnect handle built right into the inverter. It has to be labeled as a DC PV disconnect, and it also that it has a rapid shutdown feature. And the labeling is super important for future maintenance. If an electrician has to work on your house or the PV system, you need this labeling to have them know exactly what's there and what kind of hazards are there. And it can also be useful for first responders. All right, so now we're going to look at an AC combiner panel. This is where multiple arrays may be connected to be combined into one single feed before going into the interconnection. It's kind of like a sub panel, but it's slightly different. So not only does the overcurrent protection need to be appropriately sized in here, the enclosure needs to be properly bonded and grounded, and the neutral must be isolated from the enclosure. So you can see here, there's a separate neutral bar, and it's not connected to the enclosure, and the grounding wire, which is the green wire, as you would expect, is connected to the enclosure. So the enclosure is properly bonded and grounded in this system. All right, so now we're going to talk about the interconnections. First, we'll talk about a load side connection. This is kind of a simple drawing of where the load side connection is made. It's when the inverter output is connected on the load side of the service disconnecting means, which is the main breaker, basically. This is typically accomplished through the use of a backfeed breaker, which you have to locate on the opposite side of the panel as the main breaker. This is so as not to overload the bus bar. Basically the sum of the backfeed breaker and the main breaker must not exceed 120% of the bus bar rating. So the sum of this breaker plus the main breaker, if it's like a 100 amp service or a 200 amp service, can't exceed 120% of the bus bar rating. So for example, if you have a 100 amp service and 100 amp bus bar rating, you can have a 20 amp backfeed breaker and it'll still be acceptable. If it was up to like a 20 or 30 amp backfeed breaker, that would not fall within this rule. You can locate the breaker anywhere in the panel if the sum of the backfeed breaker and the main breaker doesn't exceed 100% of the bus bar rating. So this is basically to ensure that nowhere in the panel will there be more current than the bus bar can handle. So that's why, if you have power, if you have a 100 amp service and a 20 amp backfeed breaker, if you have 100 amps coming in the top of the panel and 20 amps coming in the bottom, which would only happen if you are pulling 120 amps for something, which is a lot of amps, at no point in that panel should there be 120 amps in a single place, which could, damage the bus bar or, melt it. So when looking at a load side connection, you need to look at your circuit ampacity, which is basically the max output current. So you do this by looking at the inverter nameplate and look at its output current. And you want to size the breaker to handle the breaker and the wire to handle 125% of the rated output ampacity of the circuit. So you can see here, it's a 16 amp output for this inverter. You multiply that by 1.25 because it's 125%, and you would size the breaker and the conductors to handle 20 amps. And it's crucial to size conductors correctly, because if you undersize the conductors or the breakers, you can cause damage and it could cause fires. So you definitely don't want to undersize those. And there's, once you know the ampacity that you're looking for to have the conductor size for, you can just look online. There's tables to tell you what size wire you need for a certain length of wire. All right, so the overcurrent protection device must also be properly sized. Same rule, 125% of the output ampacity. This is vital to a safe code compliant system. Here you can see the standard calculation to determine the sizing of the circuit breakers and the fuses. Take 125% of the output current, and that's how you size it. And this is to protect the wiring and the equipment in the system. As I said, most backfeed breakers will be double breakers, so they're a 240 volt, which corresponds to what's in most homes. So you'll have equal distribution in each leg. Here we see the requirements for the circuit identification. On the right side here, you see a good example of a directory for a microinverter system that includes a color-coded map right here. That shows specifically which modules are on which circuits, and it provides for easy maintenance and troubleshooting later on. And it's important, on the left, you see kind of your standard electrical panel schedule. And it's important for labeling to be legible and easily identifiable. Here you can see this is where the backfeed breaker is. It's you can read it, but it could be neater. But that's how it is. You want to make sure that it definitely can't be confused with something else, though. So here's a simple look at the common load side connection calculation that I just mentioned, the 120% rule. And that's to determine if the panel board is large enough to accommodate the PV system. So you want to ensure that the main breaker plus 125% of the PV output current does not exceed the bus bar rating by more than 125%. So in this, you have a main breaker of 100 amps, you have a bus bar rating of 100 amps, and you have an inverter output current of 14.4 amps. So you multiply that by 125%, you get 18 amps. So the main plus the PV is 118 amps. 120% of the bus bar rating is 120 amps. So 118 is less than 120. So you are okay in this situation. That's kind of an example calculation. Obviously, every system will be different, but it would follow similar rules. So the other type of interconnection is a supply side connection. This is when the inverter output is connected to the utility side of the main service disconnect. This interconnection type is sometimes referred to as a line side connection or a line side tap. Since a supply side connection is very similar to a new service entrance, the NEC requires that the disconnect be rated for such. And it has to contain overcurrent protection, fuses, or circuit breakers. At a minimum, the fault current rating should match that of the existing service equipment. And you need 60 amp rating for entrance conductors right here per code. All right. So a supply side connection must have a service rated disconnect switch with a minimum rating of 30, 60, 100, or none of the above. We're falling a little bit behind, so I'm going to keep moving through. I think everyone got it. The answer is C, 60 amps, as I just went through. So keep moving through. So also with the supply side connection, you have to ensure that the conductors are sized appropriately, as you do throughout the whole system. So you verify this by looking at the nameplate, the inverter nameplate for the max continuous inverter current output. Just like with the load side connection, you multiply that by 125%, and verify that the conductor size is stamped on the wire can accommodate that. And as I said, there's tables you can look up to verify that the wire can handle that amperage. In the 2017 NEC, which is what NYSERDA has adopted at this point, it states that the length of the supply side conductors must be no more than 10 feet in length unless other means are taken to prevent them or to protect them, such as current limiting devices. You can see here the inverter output. It starts at A, and then the connection is at B, the interconnection, the supply side interconnection, and that can be no more than 10 feet. And so you can see here at A, that's where the inverter output is fused and changed to service conductors, which are 60 amp rated, which I just talked about. Okay, so in light of the fact that the supply side conductors are similar to a second set of service entrance conductors in that they're unprotected from utility side current potentials, the disconnect that serves as a supply side connection has to be bonded similarly to a service panel where the neutral and ground are bonded together. You can see that in the photo here. This green screw is used to bond the bare ground wire and the neutral, and also this green ground wire. So that was done correctly in this situation, and that creates the bond between the neutral and the ground that allow for overcurrent protection devices to operate properly, and it also grounds the enclosure. So here's another supply side connection. The main difference here is that there's no bare ground conductor. The ground is run via the green conductors, which obviously all have insulation on them. And you can see it crimped together on the left-hand side. So this is done. The NEC requires that this enclosure and the conduit be bonded at both ends. If run in ferrous conduit, which is metallic conduit. The purpose of this is these are usually connected to the enclosure via knockouts, which are like pre-pushed through, so there's not a huge amount of connection, so it's easy to get out. And so if there was a fault current running through the conductors and it got into the conduit and it wanted to get through into the enclosure, it would likely be more than that knockout could hold, and it would melt through and cause damage and potentially a fire. So that's why you separately use these crimp connectors to bond and ground the conduit itself. All right, so here we have kind of labels, examples of labeling requirements for this type of connection. You have the traditional electrical shock label right here, and the PV disconnect label right here that you would normally see. And so you also have the disconnect label here that shows where the disconnects are for the main breaker essentially, and the PV disconnect. And so the PV part of the code is probably has probably the heaviest requirements for labeling that there is, and it's all important to maintain the safety of the system. So definitely familiarize with that part of yourself with that part of the code to ensure that these are installed safely and you know what you're looking at. So which of these options is not an accurate description of a solar PV system? I'll let you guys throw that in the chat. Maybe. We'll keep moving through here. The one that is not is a load side connection with a capacitor diverter. That is not a real thing. A capacitor diverter. You can have a supply side connection with optimizers. It doesn't really matter where the connection is for if you have optimizers, inverters, or a string inverter. You just have to everything just has to be compatible with each other, and the connection and the type of inverter is kind of irrelevant. But yeah, so it's the one with the capacitor diverter is not a solar PV system. Now we'll get into some labeling requirements, which is hopefully we can move through this pretty quick and gain back a little bit of time. So the New York State Solar Guidebook has a detailed labeling guide. It can be very challenging even for experienced contractors. So some things to remember are the labels have to be durable. They're supposed to last 25 plus years. They're supposed to be placed in manufacturer recommended areas and not covering other labels. Colors are predetermined by ANSI and OSHA, so you have to use the correct coloring. Typically, they're red, yellow, or orange. You'll never see other colors for solar labeling. And the other thing to keep in mind is the most dangerous label is a wrong label. If you have a missing label, that's bad, and it's then not very safe. But if you have a wrong label, that's even worse, because that will, if you have an electrician coming to work on your house or whatever, they'll see that label, they'll think they know what's happening and what the situation is. And if it's not that, they could potentially, do something harmful and put themselves in harm's way, and could cause shock hazards and injuries. So you definitely want to make sure that all the labels are correct. So now we'll go through some of the labels that are required for solar projects. As I mentioned, all solar PV signage is yellow, orange, or red. So it's really easy to identify for electricians and code officials. So first we have the arc flash warning. This is required on basically all electrical equipment, switchboards, panel boards, control boards, meter enclosures, motor control centers that are in other than dwelling occupancies. These are super important because arc flash incidents can cause death. And if not, it can cause serious injury or blindness or different things. So it's super important. Here we have the service disconnect labeling that's required. All service disconnects have to be labeled with permanent plaques. And here you can see it's kind of good practice to, on each of them, tell where the other one is. Because if you only shut down one, you could still have an energized system. And if you just say this is the first service disconnect, one of two, and you don't tell where the other one is, it's much less useful. So here we have for a supply side connection, NEC 230.2 requires a directory of the location of each service disconnecting means, just kind of like I just mentioned. So it can, excuse me, it can be accomplished by either a simple description on the of the location, like in the photo on the left, or a map of the building as seen on the right, showing where the disconnects are. Yeah, talking this long is it dries out your mouth. So here we have PV, AC, and DC disconnect labels. You definitely want to have a label on the PV system disconnects, and you're also going to want the electrical shock hazard labeling. Traditionally, if you shut down the disconnect to a system, the power will just be off. But if you shut off the main disconnect and not the solar disconnect, if the sun's out, you'll likely still have an energized system, and you definitely want to make that clear. And just remember, labels have to be suitable for the environment in which they're installed, and the labels should be expected to last the life of the system. And again, a missing label is bad, a wrong label is even worse. Here you have the electrical shock hazard sticker. You want to have this on all your switches and circuit breaker panels as well, so people understand there's a hazard and to be careful. So anytime you have an inverter output, that's known as an interactive system point of interconnection, and you have to label with the rated AC output current and the nominal operating voltage. Something to keep in mind is NYSERDA does not allow writing in on these labels. You want to have it engraved or printed onto the label. Engraved would obviously be on like a plaque or something. Printed would be on this kind of label. And that's because, over time, these systems are typically like in the elements, or even if they're not, they'll fade, and it'll basically the information will basically disappear by the end of the system life. And so 25 years from now, no one will have a clue what was written here. So you want to definitely make sure it's engraved or printed on. So here we have the PV power source labels. You want to have all of the DC conductors that are in metallic raceways or metal clad cable inside a building. They all have to have this labeling. Warning PV power source at a minimum every 10 feet. Many people don't like the look of this, as you might expect, but it's code, so they kind of have to deal with it. And so a way around this is they'll just run the conduit through the attic space or use microinverters at the solar panels, which convert it to AC power, which can then just be run through conduit without this label. And that's so that they can avoid having to see this red label. And also something to keep in mind is if they do run it through the attic with the DC power inside it, they still have to have this label on it. It's just you won't see it because it's in the attic. Here we have a direct current PV power source label, which must be on an inverter integrated DC disconnect or a DC combiner with a disconnect. So this gives you important information on the system for anyone who will maintain and repair the system in the future. You have to label the max voltage, the max current circuit current, my bad. And then if you have like a battery system installed with it, you want to have the max current of the charge controllers as well. Here you have another example of the PV-AC disconnect. You need the AC output current and AC operating voltage. We already went through this one. A lot of times these are missing, incomplete, or not suitable for the environment. But there are many manufacturers that make labels that will endure outdoor conditions such as wind, snow, rain, UV degradation, all that stuff. And this is required at the interactive system point of interconnection. The 2017 NEC expanded on labeling requirements with even more details. So this label alerts first responders and others that the system is equipped with rapid shutdown. The red is for string inverters, yellow is for DC optimizers and microinverters. Something to keep in mind, I don't imagine the people in Shenango County are going to be doing inspections in New York City, but who might have talked? But New York City adopted the 2008 or the 2011 National Electrical Code, which doesn't include rapid shutdown. But NYSERDA accepts the 2017 NEC, so they're able to specify a rapid shutdown be installed, even though that's not included in the current New York City minimum code. But NYSERDA can require that it be installed because they're incentivizing it. And if someone doesn't want the incentive, then they don't have to deal with NYSERDA about that. So that's something to keep in mind if you happen to inspect systems in New York City. Here we have the point of interconnection identification. This requirement is simply to identify all sources of power supplied to a bus bar or conductor, which tells that even if you shut down one of the one of the disconnects, it could still be energized, and it tells that there's multiple power sources. This is another label required by NEC and OSHA. It's pretty self-explanatory. Basically the same thing as the previous one. You need to make sure all disconnects are closed before working in the panel to avoid it being energized while you work on it. This is super important. Here's the power source output connection label, saying that you do not want to relocate this this breaker. This is an example of, like, in the 120% rule, you want to have that backfeed breaker on the opposite side of the panel compared to the main breaker. And that's to avoid overloading the bus bar with current. Here again, we see the requirement for identification of circuits. This person didn't label the circuits, which is a no-no. That's, you know, the whole point of that is to assist future electricians in their maintenance and troubleshooting work, and so the homeowner can then shut the system off if they need to. This is not part of the code, but it's just part of the general, or not part of the solar code, it's part of the general electrical code, which has to be followed for solar as well. So which of these options does not describe a PV warning label? Red background with white text, orange and white background with black text, orange background with black text, or green and white background with black text. So here we have labels or answers coming in. I think they're mostly right. So solar labels are always red, orange, or yellow. So green with white background and black text are not used for PV warning labels. All right, so photo inspections. Can a comprehensive inspection be done by looking only at photographs? The answer is yes. But the quality of that depends on the quality and comprehensiveness of the photo collection. Photo inspections are through the quality assurance program. They're done through the QA program to save dollars by not making someone go to an in-person 4-hour inspection. And something to keep in mind is well-built systems can fail a photo inspection if the quality or quantity of photos is not enough to make a determination of code compliance. So NYSERDA has been doing these types of photo-only inspections for a long time now. Permitting authorities can choose to require photos to supplement an in-person inspection to avoid making multiple trips to a site and save time and money. Photos can tell a story of how things were constructed and save the inspector time. It can improve inspector safety by reducing the exposure to hazards, like I mentioned earlier. Like they may not have to go up on ladders or access energized electrical equipment if there's photos of the equipment. You can have photos of trenches and walls before being closed to reduce the number of trips to the site. So it can be a very useful way to do inspections or supplement inspections to help, save time and money. So NYSERDA has implemented photo-only inspections with great success. As I mentioned, they can save costs, it allows the inspector to review photos, to not have to make multiple trips to a site, avoid risks, and you can also have pictures provided of trenches or walls before they're closed that might enable the inspector to save an additional trip. And also, if these are provided to the inspector kind of in a timely manner, like when things are being installed, you could catch mistakes early so that you catch it before they'll have to go back and tear everything out and redo it. For instance, if something is too close to a property line, if they send you a photo of the trenching, they can just undo that kind of and redo it instead of having to go back months later when the inspection's done and dig everything back up, dig a new trench, and you you understand. So here we go. What are some of the reasons to use photos to supplement inspection? It's like some answers are starting to come in. You are correct. It is D, all the above. We just went through this, so I won't, read through everything. I'll send you guys this, or I'll send Allison this, a PDF of this presentation so that she can distribute it to all of you too. So you have this, this information that's referenceable, if that's a word. All right, so now I think this is the most interesting part, which is good because it's the last part. So now we'll go through some of the common installation errors that NYSERDA has seen in the field through the thousands of inspections they've done. So we talked about this a couple times already, but it's important to ensure that the system grounding is done properly. It could be the clamps are loose, it could be the integrated bonding system is not compatible with the panel racking system, or you're just not using the bonding system correctly. But if the system's not grounded, it can cause serious injury or death, so it's very important. Now there are some panels that have plastic frames which don't need to be grounded, but you still have to make sure there's a good bond through the system. At the array, the bonding and grounding are very important issues, as I mentioned like 25 times in this presentation. As discussed earlier, the bonding of equipment provides the pathway for fault current to open an overcurrent device or be detected by the fault detection equipment, which will disconnect this fault from the system or from the equipment. Here we see an integrated mid clamp that provides the bonding of all modules, except for in this situation, there was a single module placed by itself utilizing only end clamps. So additional bonding methods would need to be employed to ensure bonding and grounding of that separate module, but throughout the main array, these would be sufficient. And there are other methods such as weave washers or star washers that may also accomplish bonding and grounding as well, as lay-in lugs, which we'll see in a bit more detail soon. So here we have an example of where a contractor attempted to accomplish bonding requirements with copper lay-in lugs on aluminum frames. However, as you can see, they have corroded and actually broken away from the module. So you can also see the reaction between the copper conductor over here and the aluminum frame up here. So do you think these two modules are effectively bonded together? I think the answer is quite obviously no. This is the ground wire and it's not even connected to this panel, so it's definitely not grounded correctly. And this happened just in the time between the build and interconnection and the quality assurance inspection. So by that point, which is probably months, the screw had already corroded to a point where it broke away from the panel frame. So this one is likely not far behind. And so you have to use equipment that's rated for the environment it's in, and equipment that's compatible with the panels. All of the system equipment have to be compatible with each other. So here we have a situation where they bonded the rails themselves, and you have to do that, and it's accomplished through a lay-in lug like the one pictured here. However, the lug is not installed with a screw that is listed for bonding purposes, and that's typically done with a finely threaded machine screw. The code requires that a minimum of 2 threads are in connection with the metal, and this is a self-tapping screw with pretty coarse threading. So this would fail for that reason. It doesn't have a good enough connection to the rails, so it can eventually fail. Here we have one of the most common installation errors that you would see is On a rooftop where the conductors are not properly supported and are just laying on the roof where they're subject to damage by wind, snow, ice, movement, and especially the abrasive shingles they're in contact with, right? Eventually they'll, wind will move them around enough that it will erode the insulation on the wires, and then you have a potentially dangerous situation and probably system failure. Another potential hazard is squirrels or other creatures nesting underneath the panels. It gets pretty warm underneath these, and it provides protection from rain and all that. And also they like to chew on the wires. So what you would do to prevent this is there are things called critter guards, which are basically metal or plastic mesh that surrounds the array and blocks the critters from getting between the array and the roof. And also another potential risk of this situation is the wires can catch debris, which can cause drainage issues, which can then cause problems with the roof. And obviously we want to avoid that for the sake of the homeowner. Here we have this is a correct example of how things were installed correctly, but we talked about having the correct equipment for the application. So all the conductors and fuses should be DC rated and should be rated for PV. And you can see here, this is rated for PV. So another common error is where the fittings used for conductors to enter an enclosure are missing or not installed to secure the conductors from movement. And that'll cause stress on the terminations. So on the right, the hole in the strain connector is too big for the cable, so it would fail. That would essentially do nothing to prevent these from moving all over and eventually eroding away and having stress on the terminations. So that would have to be switched out and, for a tighter connection. And in the enclosure on the left, the flashing is good. It's up under the shingles, looks good. However, there are manufacturer knockout locations in this enclosure, and they were not utilized, right? They just ran the wiring up underneath the top, which would be installed on top of this, and you can't do that, right? Because that unseals, it makes it not weather rated, and eventually moisture will get in and water, and you have water damage, and obviously you don't want to have water in your electrical system. So that would definitely fail. They should disconnect these, run them all through the knockouts and have a proper fitting, and accomplish getting the connection in the enclosure that way. Also, the red wire nuts and possibly the blue ones are not rated for outdoor use, even though it's in an enclosure. It is an outdoor location. The humidity and the temperature are going to be the same as outside the box, so it's still considered an outdoor environment. So many contractors underestimate the effects of galvanic corrosion that happens with the direct contact of dissimilar metals. You can see that starting way up here on the right, and you can see it well underway on the left. So the copper conductors are in contact with a dissimilar metal in a wet location, and you can see that they're corroding and deteriorating. A way to avoid this would be to use insulated conductors or other methods to prevent the touching of those two metals. This one isn't that bad yet, but it will continue to get worse and worse until it corrodes away, and then you don't have a ground path. Excuse me. Here you have another example of the same thing. You have a raceway that's being used to support a conductor, which is against code. The only time you can do that really is for like data wires. And also you see the galvanic corrosion again between the copper conductor and the coating on the raceway. So again, this will corrode until there's basically nothing left. And it'll probably corrode in a lot of places because it's supported, supporting this copper wire. So it's going to eventually deteriorate, and then you're going to have no ground connection again. Here, you see these conductors in the image are not protected from physical damage. Notice the sharp edge of the racking and also the edge of the shingles. The abrasion on these two surfaces will eventually cause the conductors to be worn down, and they'll fail, well before the 25 years that this should be designed for. So this contractor should have used conduit to protect those conductors going around, from the panels around and off the roof. Here we have an example of a common issue with an enclosure itself. Code allows for the use of what's called weep holes, which effectively allow water to exit an enclosure to avoid pooling. Weep holes are used to prevent moisture from accumulating in an enclosure. You don't want it to be pooling in an electrical enclosure for obvious reasons. So here you can see that the water line ends where the weep hole is, so that shows that this was effectively draining the water. And obviously you want to make sure that these are not sealed, as they're specifically for allowing water to leave the box. Here, excuse me, we have an interesting situation. We have an outdoor rated enclosure that was simply not installed properly. You can't really see it in this picture, but the conduit entry point isn't properly sealed at the top of this enclosure. So what you have is you have water that gets down into the enclosure, and it pools in the bottom of the junction box, and eventually it gets high enough that it drains down one of the side conduits, and then it's going through your electrical system, potentially causing havoc. So you want to avoid that at all costs. This would have to be fixed, and the only way that they were able to find that this happened was this inspection was done in the winter, so it was filled with ice instead of water. So it's important that everything be installed correctly when it's installed. All right, here we have an enclosure that's not only suffering from water buildup, as you can see. The lugs on the conduit are not rated for a wet environment. You can see over here, it's rusting. And the wire nut terminations are also not rated for outdoor environment. This is a location that would be well served by the installation of a code compliant weep hole to drain the excess water. And on the right, we have, these are the same place. So this is on the far right, it's just a close up of right here. But this is a flat roof with panels installed on it. And you have the conduit that comes out of the box and it's bent up to get over this rail. And what that does is, if it ever rains, the rain will get in that conduit and it'll just go all the way down right into the enclosure. So it basically acts as a highway for water to enter the electrical enclosure, which again you want to avoid. Here we have conduit passing from the outside of a building to the inside of a building that was not sealed. You would want to seal that with some kind of insulation. This not having that sealed has a potential for condensation to build up where warm building air meets the cooler outside air, or vice versa. And once that condensation forms, it has no place to go but down the conduit into the panel board, or whatever's on the other side of this wall. So again, you want to put some kind of insulation in there so that the hot or the indoor air and the outdoor air don't mix. And this is a violation of the general electrical code and of the energy code, since there's an energy component to it. So here, we saw an example of this earlier. If you have a metal conduit that's between two non-metallic enclosures, within this enclosure, you would want to have it have the conduit bonded. And in this case, this is a metallic enclosure on the inside, and not metallic on the outside. So you want to have a ground bus or a grounding wedge that has to be installed inside the enclosure to properly ground it and bond it. All right, so here's a kind of an interesting one. Here we see on one of the non-contact voltage testers being used to determine if the disconnect is wired backwards, and it is. So this is an open disconnect, and the bottom of the disconnect is still energized. So what that means is the conductors were installed in the opposite way that they should be, and that means that the fuse is always energized. So you basically don't have a safe way to replace the fuses if you ever need to. The wires that are terminated at the top should have been terminated at the bottom, and vice versa. And one thing to keep in mind is these non-contact voltage testers don't always work with DC voltage. So if you have a DC disconnect, you want to make sure that you're not relying solely on a non-contact voltage tester, because it may not show voltage. So here we see a supply side disconnecting means that has proper neutral and ground bond in accordance with the code. This was actually done correctly. You can see here the white neutral conductor entering from the top on the left side, and the green bonding screw effectively bonding the neutral to the enclosure and to the ground. So that was done correctly. Here you have terminal lugs where you land wires that are rated, terminal lugs where you land wires are rated for conductor size and max number of conductors. These are rated for one conductor, and someone tried to sneak in a separate second conductor, which is against code. So here you see right over here, you see the main breaker where conductors have been doubled up, and here you just see breakers where they've been doubled up. So that is not allowed. You have to follow the requirements of each piece of equipment. So Article 705.12b covers the requirements for load side connections. This label is required for when the 120% rule is being used to add additional PV current to the bus in excess of its rating. This requires that if you're going to add additional power to the bus, that the source of PV power must be at the opposite end of the bus so as not to overload the bus, as we've seen already. And you need a bunch of labels in this situation, which you can see here. Here's kind of a not super common system or configuration, but you might see it. So here's feeder taps that are a type of interconnection that require kind of special consideration. It's sort of like a hybrid load side connection. They have the potential to add additional available current to conductors and bus bars, and we need to consider this. So in this case, in order to protect the conductors from additional PV current, an additional overcurrent protection device must be installed. This is covered in Article 705 of the code. And so here's a real life example of the previous slide. So you can see the interconnection on the load side of the 200 amp breaker in an apartment where the apartment panel didn't have a main breaker, and you have the meter pan with an integral disconnect. The existing conductors and possibly the bus bar downstream can be strained by this additional current. So possible solutions include connectors in the bus bar being increased in size for the new additional current, or additional protection by adding an overcurrent device before the loads, such as a main breaker in the panel, the speeds. That's all expensive. You would have the PV voltage tapped into the utility side coming in, and those taps connected to a disconnect. Then you would have a main breaker on your electrical panel so that you don't overload your panel. This is not very common, but there are places where you need it, like for instance in apartment panels, like we've talked about. So here we have a situation where this roof penetration was not properly sealed. The contractor drilled through the roof, and then rather than sealing it properly, which you would use this piece of equipment to properly seal it, as we saw earlier, they used what's called duct seal, or sometimes called dum-dum, for a reason, to seal the opening. It doesn't look great, and it's basically putty that goes around the hole. It's somewhat weatherproof, but it's not being used correctly here. It shouldn't be used, permanently for this kind of application. Here we have, this is probably the most interesting error that we have in this presentation. So these two pictures are of the same panel. Here you can see they're an outdoor panel. Here you can see the left lug looks pretty good. The right lug is discolored, and the insulation for the conductors in very bad shape. So what happened here is the right lug was not tightened down correctly, and the wire was loose in the lug. So it didn't have a really good connection, and the temperature of the wire would go, back and forth, hot and cold, hot and cold. And then it eventually burned off the insulation. And then since it's outside, condensate got in there and caused the copper to corrode and flake off. So the only way to fix this was a complete replacement. We have no idea if the copper shards fell down into the panel behind the breakers, causing areas that could fail. So the only way to fix it was the contractor had to replace it all. So that lug should have been torqued down to the value specified by the manufacturer. That's part of code. But that's kind of, an interesting situation. It's not likely you'll see it all that often, but you definitely, this is obvious that there's something not right when you look at this panel. So keep an eye out for that stuff. So there are also structural considerations for electrical panels or solar panels. Here we have a situation where there was a natural gas explosion outside of Boston. It's one of a few homes that was impacted by this. Some people think that the racking used on the roof for these solar panels can actually make the roof stronger. And this situation sort of emphasizes that. It shows there was a natural gas explosion and the roof is generally intact, which the other roofs that were affected by this were not. So it's just kind of included here for interest. Structural issues should be addressed by a New York State licensed PE or registered architect, as I mentioned like 50 times. So that's just kind of interesting. Here's a couple products you may see, probably not likely. This one was being installed in the Con Ed territory. It's what's called a Connect DER, which can eliminate, it's used to provide information to the utility on solar power that's being put back into the grid. It can help them forecast how much power they're going to need from, power plants and all of that. And it can eliminate costly interconnections, sorry, and reduce installation errors for supply side connections. This was, as I said, experimented with in the Con Ed territory. This is installed by the utility. It's the point of interconnection for the PV system. And it, like I said, gives the utility real-time solar generation data. And this requires that the connection be made in the meter pan. 2020 NEC will require that all meter pans, or it does require because it exists now. It requires that all meter pans have non-fused disconnect switch so that the meter can be serviced, and this could change where the connection point is for a lot of systems. And also this is handy because it allows the contractors installing your PV to stay outside your home, and they don't even have to come inside your home to install the whole system. So that's handy. Here's another new product, or it was new when this presentation was made, but it's called micro flashing. It's designed to reduce the amount of work anchoring the systems to existing roofs. I don't know if they'll be super common that you would see those, but they're out there, and that's why we've included it here. Normally you would not want an electrician doing the flashing on your roof. You'd want a roofer to do that, but in these systems, to prevent having multiple trades on site, they'll have the electrician take care of it. And I've heard feedback from people that do the installation of these things that they are super useful, and they work really well. So maybe you will see them more commonly than I think. So we have 2 slides left. Here are a bunch of additional resources that NYSERDA has. They're really good resources. You have the solar guidebook. We've talked about that extensively today. There's also the quality assurance checklists and guides that are available through NYSERDA's website. And lastly, there's the energy storage guidebook, which is also available through NYSERDA. And these are all available publicly, and you're welcome to take advantage of those. Energy storage is likely to be more common moving forward. There's a energy storage roadmap that NYSERDA released, where they are planning to incentivize battery systems in homes. So they could become more common, and if you see something like that, this energy storage guidebook is a great reference. All right, so this is the last slide. This is Hudson High School, and they have a solar array on their property, as you can see right here. And it's a 1.2 megawatt array, and it's a little bit bigger than the athletic field surrounded by the track. So this is just kind of a good visual for how big these systems are. So a megawatt system would likely be about as big as a football field with a track around it. So it's just kind of an interesting visual for you. And if we're like basically out of time, I just made it with 1 minute left. But if you have any questions, you can email cleanenergyhelp@nyserda.ny.gov. That goes to all the people on the clean siting team, so it should get you an answer pretty quick. Or you can email me. My email is on the first slide of this presentation, which again, I'll email to Allison, and she can get it out to everyone. If there are any questions right now, I can try and answer them real quick, but I'm assuming you guys don't all want to stay super late. So we can wrap it up if there's no questions. Also, I see 2 people put in their New York State training ID to the chat. So thank you for that. If anyone else needs credit for this, please put your information in the chat so that we have it. And so it doesn't look like there's any questions in the chat, so I will let you all go. And thank you for attending, and have a great day or great night now. But thank you.
Thank you, Chris. Just a quick question. Do I need to have that training code, or is that strictly for you?
So that's probably for me, because I'll send this to send this to the Department of State, and along with the attendance list, and they will allot credit based on
Okay.
it.
I just wanted to make sure because it didn't come through to everyone, those codes. So just making sure.
Okay. But yeah, so and if for some reason you don't know what your number is and you can't put it in the chat, either email me or email Allison and she can get it to me. But all right. Thank you all, and I will let you go.